Hello everybody, hope everybody is doing great. CRS here. This video is concerned with discussing about Kepler's laws of planetary motion. It has been quite a long time since humanity has been gazing the night sky, and we have always been very curious. Even when we were children, we used to ask a lot of questions about the sky. It's time we answer some of them. Dear friends, let's begin with what the planets do around the sun. We all know that they go around the sun, and how do they go around the sun is some clarity that we are going to get with this lecture. With that, we will also be understanding how much time it takes for the planet to go around the sun and how general is this law. Can this also be extended to satellites that orbit planets? This is the second question we are going to answer during the course of the video. So let's begin without much ado. So the law of orbits, which is the first law of Kepler's, says that all planets revolve around the sun in elliptical orbits with sun at one of the foci. An ellipse, unlike a circle, has two foci, two centers, and this particular point is what is known as a focus, and the sun is always at one of the foci. Let's try and understand this. We have an ellipse here, and let's say I have a sun at one of these points. Here is the sun. This is the other focus. This is one focus. There are two foci. Let me just fill the sun up. So that's the sun. You can have a planet, and the planet is revolving around the sun, and you see that the speed of the planet is actually not uniform. Here it slows down, and then here it speeds up, and then slows down and speeds up, and so on. So the planets, of course, go around the sun in elliptical orbits, and in addition to this, these ellipses need not be in the same plane. For example, if this is the plane in which the Earth is orbiting the sun, it need not be the same plane in which Saturn orbits the sun. So they could be in any orientation for that matter. In general, yes, of course, it's quite a flat plane in which all of these planets orbit the sun, but then they are not perfectly aligned. That's my point. In addition to this, there is something that I'd like to convey. If you watch from here, you will see that the Earth orbits the sun in this plane. So that's the Earth, and here is the sun, and the Earth orbits the sun like this, and what you're seeing here is just that plane. The moon orbits the Earth in this plane. So the moon is going around the Earth like that. So here is the Earth, and the moon is going around like that. The angle, there is a certain angle that these two planes make with one another. Well, having understood that, the 2 points at which the moon's orbit cuts this plane, the plane in which Earth orbits the sun, are the points which are called Rahu and Ketu. Well, long ago, we Indians already knew that these two ellipses are not in the same plane, they are at an angle, and that's how we exactly know that there are 2 points at which the moon's orbit cuts the plane in which the Earth orbits the sun, and these two were named Rahu and Ketu. Every time moon occupies that point, you will have an eclipse. If it is a new moon day, then you can have a solar eclipse, because moon is in between that of the sun and the Earth. And if you have a full moon day and you have the moon at one of these 2 points, then you have a lunar eclipse. This is exactly how we understood, how much we understood about the orbits of different planets and satellites around the Earth. Having understood this, dear friends, let's go to the next law. Kepler stated the next law this way. It's called the law of areas. Law of areas says that a position vector drawn from the sun to a planet sweeps equal areas in equal intervals of time. Let's try and write that ellipse and get an understanding of that. So here is an ellipse. Let me make that look a little bigger. And then I have the sun. Here is the sun. And the sun, okay. So we have the sun. The planet is right now here, let's say. You draw a position vector from the sun to the planet. Let the planet now go for a while, let's say about a month or so. Okay, and when you do that, the planet now comes to, let's say, this place exactly 1 month later. Now the same position vector must be drawn from here to here. Well, you can see, you can shade this particular part. The shaded part is the area swept by that position vector in 1 month. Now leave about 6 months or so. Let's talk about the earth, and earth has probably reached somewhere here, right, about 5-6 months later. So the earth has reached here. Let's draw another position vector to this place, right? Sorry, let's draw another position vector to this place. Well, here, and then exactly 1 month later, you will see that earth has come here. Exactly 1 month later, you will see that the earth has come here, and let's draw another position vector to that place. So that, if you just see how much area now that position vector has swept. In the first case, planet moved from point A to point B, and this was the area. Let me call that A1. In the second case, the position vector went from point P or maybe C to D, and the area in this case, let's say, is A2. And in both cases, we have observed the earth move from one point to another point in a month's time. So from here to here, about 30 days. From here to here, another 30 days. You will see that the area swept in the first case is equal to area swept in the second case. So this is what is law of areas. Now the only thing that we've got to do is do some physics with this and try and understand why is this particular reality, this particular law a reality. Let's try and figure this out. Let's start with something that we can easily understand. Let's take a circle, and this circle is the orbit of the earth. Let's assume that's the orbit of the earth. Here is the sun. Let me just mark that by writing S. Okay, and then I shall draw a position vector from here to this place, and then from here to this place, because the earth has moved by a very small angle. This small angle, dear friends, is, let's say, d theta. D theta is the tiny angle by which it has moved. If that is the case, and S is the distance that it has traveled, S is the distance, this d theta is such a small angle that you can say that ds, or rather the tiny bit of distance that it has covered, ds, is essentially almost a straight line. So if you ask me, sir, how do you calculate the area? Very simple. The area is now, we call the area A or dA because it's a very tiny area. It can be written as half into base into height. Half into base. Base is this length. You can write that as ds. Into height. Height is nothing but the radius of the Earth's orbit in this case. So you can write that r. Now ds is the arc length, and it can be written as r into d theta. You substitute that there, dA becomes equal to half r square d theta. Well, let's understand the statement of Kepler's second law. It says it sweeps equal areas in equal intervals of time. That means we'll have to look at how does the area swept dA change with time. So let's find the rate of change of that area. So I have dA by dt equal to half. R is a constant in this case, and we have d theta divided by dt. So we have dA by dt being equal to half r square into omega. In order to make sense out of these quantities, let me just multiply and divide by m, where m is the mass of the planet, in this case the mass of the earth. If I do that, I have dA divided by dt equal to half into r square into omega multiplied by m by m. But you know what? Half r square omega m by m, m omega r square out of this, m omega r square out of this is what is known as angular momentum, of the planet, the earth. And when the angular momentum is written, in conservation of angular momentum, you have learned that unless there is an external torque, angular momentum is going to remain a constant, and we have the earth going around the sun. There is nobody applying a torque from outside. Yes, there could be tiny forces that are acting because the distances are massive, the forces are going to be really less, you should neglect them. Then the angular momentum is practically a constant. The moment you substitute that there, you have dA divided by dt equal to L divided by 2m is what you have, irrespective of whether it's a circle or it is an ellipse. The angular momentum will remain the same. If the angular momentum remains the same, mass of the planet certainly is not going to change out of the blue. It wouldn't pop up to be something else. So this ratio will remain a constant. So aerial velocity, which is dA by dt, will remain a constant. Now this is a realization. This is essentially conservation of angular momentum, my dear friends. So of course, m omega r square, I said, is angular momentum. You can write omega as v divided by r. V equal to r omega is the equation, and you substitute it there. You have m v divided by r into r square equal to L, or L becomes equal to mvr. Another way to calculate the same angular momentum. Let's make sense out of this equation. Well, you have the velocity of the planet at two different places right now. Let's say that the planet here is at point A and it has got a velocity v. It's got a velocity v, or v1, let's say. And nevertheless, there is the sun at one of the foci. That's Kepler's first law. And then let's assume that the velocity here is something else. Let me write that velocity v2. Because the angular momentum, I said, is conserved, L1, which is the angular momentum here, must be equal to angular momentum here. So L1 would be equal to L2. That means M into V1 into R1 would be equal to M into V2 into R2. I did not write M1 and M2 because it's the mass of the planet, it remains the same. M gets cancelled. That means when R decreases, V increases. That's the reason why when R increases, velocity is lesser. When R decreases, velocity is higher. In these cases, v1 is the velocity at point A, and r1 is the distance from the sun, and r2 is the distance from the sun when the velocity is v2. This is the point at which the velocity is maximum, and that is the point at which velocity is minimum. This is the understanding that you can have just by sitting at the comfort of your room, and this is the power of theoretical physics. That you can say that at this real point in space, the planet would be moving the fastest, and there it would be moving slowest. Conservation of angular momentum has got the role to play. Having understood this, my dear friends, let's continue and talk about the third law, Kepler's third law. Let's see what does Kepler's third law state. The Kepler's third law is also called the law of periods. It's got to do with how long does a planet take to go around the sun once. Now that's exactly what's time period. it says that the square of the period of revolution is directly proportional to the cube of the semi-major axis of the ellipse along which the planet moves. Now, sir, what is a semi-major axis? Let's try to figure out. So here we have an ellipse, and I draw a line here. Let's say this is the longest chord, and that's what is the major axis. The half of the major axis is what is the minor axis. Sorry, that it's the semi-major axis. This would be the minor axis. That's the minor axis. This is the semi-major axis, half of the major axis. Anyway, the square of the period of revolution is directly proportional to cube of the semi-major axis. So this is a proportionality. Sometime later in some other video, we will look at what this equation exactly is shortly. But right now, you can just say that T1 divided by T2, the whole square, is equal to A1 divided by A2, the whole cube. That's exactly how you write the law in the language of mathematics. T1 divided by T2, the whole square, is equal to A1 divided by A2, the whole cube. Well, this is something that keeps repeating in different competitive exams, especially the ones that are easier. The CET exam, the Comet K exam, if you are in Karnataka, elsewhere, NEET exam also, this is quite a recurring question. The JEE questions could be a little tougher. We will look at those questions in another video. But then we will look at an application of what we have just learned. A satellite which is a geostationary. Now the question is, sir, what is a geostationary satellite? A geostationary satellite is one which has the same period as that of the Earth. Earth rotates once in 24 hours. The satellite also rotates exactly once in 24 hours. That means if it is above India, it will always remain above India because both of them are turning at the same rate. So this is what is a geostationary satellite. So we know that the time period T1 maybe is 24 hours. Is 24 hours because the question says that it's a geostationary satellite. Which is a particular orbit is taken to another orbit. Its distance from the center of the Earth in the new orbit is twice that of the earlier orbit. So here I have planet Earth, right? Let me fill that up. That's planet Earth, and you see the satellite was traveling in this orbit, but then later this distance, the mean distance from the Earth, has now been doubled. The mean distance from the Earth has now been doubled. I'm not talking about any distance out there. The mean distance would be the distance of the length of the semi-major axis. So that has doubled. The time period in the second orbit is, that's the question. So if the time period in this case, let's say, was T1, what is the time period in the second case? That's the question to you. So let's find out what's T2. Very easy job to do. You have Kepler's third law already at rescue. So we have T2 by T1 the whole square being equal to A2 divided by A1 the whole square. So what do you have? Well, T2 has to be figured out. Divided by T1 is 24 hours, the whole square, equal to. The radius in the second case is twice that in the first case, the question says. So the A2 is the final radius. The final radius is twice the initial radius. And A1 is the initial radius, which is just A. You'll see that A and A simply gets cancelled. And there is a cube that I forgot to write. Okay, so T2 divided by 24, the whole square, dear friends, becomes equal to 2 cube. Then what does T2 square become equal to? It becomes equal to 24 square into 2 cube. Well then, if you just ask me, sir, what's the final answer? The final answer would simply be T2 equal to 24 multiplied by 2 to the power of 3 divided by 2. Now that's your answer. That's the new time period of the satellite. It's no more geostationary. What you need to understand here is that the time period only depends on the distance. of the satellite or the planet from the sun. If you had Jupiter and Pluto exactly at the same distance, then they will simply have the same periods. But this is an understanding, that's an insight. A collection of such insights will help you answer all qualitative questions in the exam. So it's very important to carry common sense into the exam hall. These videos, which are not very mathematically intricate, will teach you stuff that you have to store in your head in a table called insights. Having said that, one last piece of information before I conclude this video. Saturn in Sanskrit is called Shaneshchara. The reason why it's called Shaneshchara is because it means the one who moves slowly. Shaneshchara means the slow mover. This simply tells you how deep was the understanding that the Indian astronomy had long before the West could evolve. We called it Shaneshchara. The only planet that's farthest and visible to the naked eye is Saturn, and we knew it moves the slowest. So, my dear friends, it's time to be really proud because we knew more than the rest and have the same feeling with you. And do remember, before I conclude this video, the day you stop growing is the day you start decaying. Thank you. Hope you enjoyed the video.